Okay, students, Assalamu alaikum. Today we are going to start our next topic for fluid mechanics, which is basically the flow in conduits. Now, if I just give you a little brief about what we have done so far in fluid mechanics, we started with chapter number 1, which was basically basic introduction of fluid. So we discussed about what is fluid from the perspective of engineering. We talked about the engineering definition of the fluid. Then after that, once we are done with the fluids itself, the definition of the fluid, we move over to the properties of the fluid in chapter number 2. So in chapter number 2, what we did is that we discussed the fluid properties, and we discussed those properties in detail. And then after that, we start moving towards studying fluid mechanics. So in the fluid mechanics, the first thing comes is the fluid statics. So in chapter number 3, we studied fluid statics. And after that, we continued with the fluid dynamics portion from chapter number 4 onward. So in chapter number 4, within fluid dynamics, the first thing was to study the fluid kinematics. So we studied fluid kinematics in chapter number 4. And then from chapter number 5 onward, we studied chapter number 5, 6, 7 as the fluid kinetics. So chapter number 4, 5, 6, 7 together makes up the fluid dynamics. And along with chapter number 3 as fluid statics, we have the complete basic studies of the fluid mechanics completed till chapter number 7. So we completed chapter number 7 in our last lecture, and in this lecture we are going to start with some applications of what we have already studied till from chapter number 1 till chapter number 7. So anyways, this is basically chapter number 10 in the textbook, but we are going to study it now. And this chapter is basically about the flow in conduits. Okay, so the first thing is that what is conduits? Conduits is basically any pipe or any conduit is any structure through which the flow can proceed. So, for example, if I have a pipe and the fluid flows through that pipe, okay. So this pipe is considered as a conduit. Now, this pipe could be circular in cross section. This pipe could be a rectangular, could be triangular, could be hexagonal, whatever be the shape. Okay. But if there is any specific pipe through which the fluid can flow, basically this conduit is an English word, okay, and it comes from the word conducts. Okay, and conduct means to pass on. Okay, so like for example, in case of the heat transfer, we say conduction heat transfer. So when the heat is transferred on pass on from one point to another, that's conduction. Okay. So conducting something is to allow something to pass on, allow some information to pass on, allow some fluid to pass on. So the device which allows the fluid to flow from one point to another is basically the conduit. So this is the thing that we are going to study in this chapter, flow in conduits. So our basic topics would be the flow classification. Then we are going to move towards the standard size for pipes, which is known as the nominal pipe size. Then we are going to talk about the pipe head loss, and then stress distributions in pipe flow. Then we're going to move towards laminar flow in round tube, turbulent flow in round tube, Moody diagram. Moody diagram would be very important here. Then we're going to talk about the minor head loss, the combined head loss. We talk a little about the non-round conduits, and then we're going to talk about the pumps and the system of pipes. So these are the topics that we are going to cover today in this chapter. So let's start this chapter. Flow classification. Conduit is any pipe, tube, or duct that is completely filled with the flowing fluid. Okay, so this is one important point here, that it should be completely filled with the flowing fluid. Okay, so there should not be any free surface. Okay, free surface is there when you have the fluid in connection with when you have the liquid in connection with the gas, or when you have more than two fluids which are flowing together or present together at the same time. So if I have a pipe, so this pipe, if completely filled with that fluid, then this is known as a conduit. Okay, so it is any pipe, tube, or duct that is completely filled with a flowing fluid, i.e. pipeline transporting liquefied natural gas, a microchannel transporting hydrogen in a fluid cell, a duct transporting air for heating of a building. Okay, so first of all, when we're talking about flow in a conduit, okay, one thing is there, what is the definition of a conduit? This is something important for the short questions point of view. What is a conduit? Okay, and the word which I'll be looking for will be completely filled. Okay, so you whenever you write the definition, you have to mention the words completely filled. Then the definition of the conduit will be complete. Okay. Now, the next thing is that since we are talking about the flow classification, so the basic flow classification that we are going to discuss is basically the laminar versus turbulent flow. Okay. So when we talk about the flows within conduits, laminar flow is basically a flow. Okay, how do we determine if the flow is laminar or turbulent? Is based on the Reynolds number. Reynolds number is something that we studied in the earlier lectures. So the formula for Reynolds number is velocity into diameter by kinematic viscosity, or density into velocity into diameter by dynamic viscosity. So this is the formula for the Reynolds number if we know the velocities. Suppose if we don't know the velocities, if we know the flow rates. So if we know the volume flow rate, then the formula for Reynolds number is this. And if we know the mass flow rate, then the formula for the Reynolds number will be this. So these are basic formulas of Reynolds number. The formula sheet will be provided to you in the exam, where the formulas of Reynolds number will also be there provided to you. But yes, you should know that what does each and every term within this formula means, because you will be provided the formula without mentioning that what does Q stands for, or what does this D stand for, or what does this mu stands for. So you should know that what are these variables within the formula. You should know it yourself. Okay, but the formula is something that will be provided to you in the exam. Okay, so when we are talking about the flow in a conduit, then the basic the basic parameter which actually differentiates between a laminar and turbulent flow is the Reynolds number. So we're going to check what is the Reynolds number of the flow. If the Reynolds number of the flow is less than or equal to 2000, then we will consider it to be laminar flow. This is for the case of the conduit. If you have a conduit, any pipe, any duct, and you find out that the velocity, the Reynolds number of the flow inside that conduit is less than or equal to 2000, we are going to consider it to be a laminar flow. Talking about the turbulent flow, it should be greater than or equal to 3000. So if the Reynolds number of flow through a conduit is greater than or equal to 3000, then we are going to consider it to be a turbulent flow. Okay, now here comes the point that what will be the case if the Reynolds number comes in between 2000 and 3000. Okay, so what would be the case? The thing is that between 2000 to 3000, it is the transition phase. Transition phase means where the flow is being converted from the laminar to the turbulent. Okay, now in this phase, it's quite unpredictable. Okay, sometimes the flow behaves as a laminar, sometimes the flow behaves as turbulent, and there is no specific correlation which can simplify, which can simply determine the flow parameters and properties during the transition stage. So the transition stage is something that we are not going to focus right now within our course. Yes, there are experiments, there are researches done by a lot of scientists in this field for the transition flows, but this is beyond our scope of this course. So we are not going to focus over the transition flow. So mostly the problems that will be there in front of you will be either covering the laminar region, or you will be focusing over the turbulent flows, but you won't have the cases of the transition flow during the course of this during this course. So this is about the flow classification. It's laminar versus turbulent flow, and it will be dependent based upon the Reynolds number, whether the flow is laminar or turbulent, for you to judge. So if anybody have any question regarding it, you can ask. Okay. Now, this is one classification, whether the flow is laminar or turbulent. The other classification is the developing versus fully developed flow. The thing is that, suppose if I have a pipe here, suppose this is a pipe, and the fluid is entering from a container or from a tank into the pipe. Now, once the fluid tries to enter into the pipe, initially what happens is that all the layers of the fluid have the same velocity. Okay, so what will be the velocity profile? It would be a straight line. But the thing is that as soon as the fluid enters the pipe, so the layer of the fluid which is in contact with the pipe surface, since the pipe is stationary, that layer becomes stationary. Okay, so that layer becomes stationary, and similarly the top layer becomes stationary. Similarly, the bottom layer, or all the layers which are there basically at the periphery of the pipe, will become stationary. However, the central layers are still moving at a high speed. Now, the thing is that all the layers are connected together with each other. So once the top layer becomes stationary, it starts dragging the other layers. So the velocity of the other layers start dropping as well. So initially what will happen is that our velocity profile will something look like this, where we have zero velocities at the edges, and then we have larger velocities in the central section. And then the effect of this drag, the viscous effect, where the layers drag over each other, okay, this is going to be increased, and as a result, the velocity profile will start developing. So this is basically the underdeveloped region where the flow is actually developing, okay? And a time will reach when the velocity profile will be perfectly developed, and we call it fully developed flow. In case of the fully developed flow, the velocity profile, something looks like this, okay, where you have the maximum velocity in the central layer, okay, in the middle layer, okay, and then you will have at the edges zero velocity, and throughout from the edges to the center, the velocity variation is there. Okay, so you won't have a region where you have the same velocity between two adjacent layers. So between any two adjacent layers, you will have a velocity variation, and that will be there. And once you have a situation like this developed, this is known as the fully developed flow. So before that, you'll have the developing flow. After that, you have the fully developed flow. So in case of the fully developed flow, you have the velocity profile well developed. Okay. In case of the developing flow, the velocity profile is continuously changing. It's developing. The effect of viscosity is being propagated, is being extended towards the entire flow throughout the entire cross section of the pipe. So you see here, as the fluid is entering, all the layers are initially moving at the same velocity. So in the central region, there is no effect of viscosity, because the viscosity of the effect of viscosity comes when the layers move at a relatively different speed when there is a velocity gradient. So initially there is a region of inviscid flow region where the effect of viscosity is not there. But then the inviscid flow region keeps on decreasing. A time comes when the inviscid flow region is actually vanishes, it finishes. And then when it is fully developed flow, then there is no inviscid flow region. So viscous effects are there from the top to the bottom over the entire cross section. So there is no region where you don't have the viscous effect region, where you don't have the viscous effects. So in the developing flow, you have the inviscid flow region. So these are the inviscid flow regions where the viscous effects are not there. So anyways, this is another classification. The first classification that we discussed was laminar versus turbulent flows. The second classification is the developing versus the fully developed flow. So whenever the fluid enters into the pipe, there is always a specific length, there is always a specific length. We call it LC, which is the for the developing flow. This is not LC, this is sorry, LE, and we call it entrance length. We call it entrance length. So entrance length is there in the developing region, and once entrance length has been passed, then it is the fully developed flow. Now, how to determine the entrance length? The formula for the entrance length is this. Entrance length divided by the diameter is equals to 0.05 into Reynolds number. This is for the case of the laminar flow. For the case of turbulent flow, it's simple formula. It does not depend upon laminar. It does not depend upon the Reynolds number. So, so entrance length divided by diameter is equals to 50. That's the formula if it is turbulent flow. But if it is laminar flow, then entrance length divided by diameter equals to 0.05 into Reynolds number. That's the formula, but this is for the case of laminar flow. So if it is a laminar flow, this is the formula. If it is a turbulent flow, then this is the formula. Anyways, these formulas will also be provided to you in the exam if needed in the solution. So that's the other classification, developing flow and fully developed flow. If a question comes in the exam as a short question or conceptual question, that how do you differentiate between a developing flow and a fully developed flow? So what will be your answer? So your answer will be, in case of developing flow, you have a changing velocity profile. The velocity profile is continuously changing. So here it was like this. Then furthermore, it was like this. Then further, it is like this. When it is fully developed, then it is completely like this. Okay. So, and once it is fully developed, then the velocity profile does not change. It remains the same throughout. Okay. So, in case of the developing flow, we will have a changing velocity profile and wall shear stress. In case of fully developed flow, we have a constant velocity profile. This is one difference. The second difference is that in case of the developing flow, we have inviscid flow region. So you see the dotted lines here. This is the inviscid flow region. So you have the inviscid flow region where the viscous effects are not there in case of the developing flow. But once it is fully developed, then there is no inviscid flow region. The viscous effect is there throughout the entire cross section of the pipe. Okay. So these are the two differences between the developing and the fully developed flow. So if in the exam comes that how would you differentiate between a developing and a fully developed flow, that's the difference that you have to write down. Okay, so let's have a numerical associated with it. Let's try to solve a problem associated with this case. Consider fluid flowing in a round tube of length 1 meter and diameter 5 millimeter. So we have a length 1 meter and diameter is 5 millimeter. Classify the flow as laminar or turbulent. So first thing is that we need to classify whether it is laminar or turbulent flow and calculate the entrance length. Then we have to calculate the entrance length. Okay, so this is LE that we want to calculate. For air with a speed of 12 meters per second, so velocity for the case of air is provided. This is the mean velocity, obviously. Okay, and water with a mass flow rate of m.8 meter per second. So for part A, we are given the velocity. For part B, we are given the mass flow rate. So this is the thing. So the thing is that we have a pipe, a round tube, length is given, diameter of the pipe is given, and we need to find two things, that whether the flow is laminar or turbulent. This is the first thing. The second thing that we need to find is what is the entrance length, okay, for this pipe flow, okay. And we have to solve for two cases. One case is when air is flowing at a velocity or the speed of 12 meters per second. And in the second case, if the water is flowing with a mass flow rate of 8 grams per second. So this is the problem statement. Before moving towards the problem solution, first of all, do you understand the problem statement? Or is there anything within the problem statement which is not clear? This is in the form of a diagram shown. This is a pipe. Length is 1 meter. Diameter is 0.005 meter. And there is fluid flowing through the pipe. We have to solve for two cases. One case is when the air is flowing with a velocity 10 meter per second. Other case is when the water is flowing with a mass flow rate of 0.008 kg per second. The temperatures of the air and water are given so that you can go into the table and you can find out the properties of the air and water. For the case of air, the viscosity of the air or kinematic viscosity of the air comes out to be this. For the case of the water, the dynamic viscosity for water comes out to be this. Anyways, for the case of the exam point of view, either the table will be provided to you so that you can go and check the value from the table, or directly the value will be provided to you in the problem statement. So let's see the solution. So part A, when we are solving it for air. So first thing is that we need to check whether the flow is laminar or turbulent. In order to check that, we need to find out what is the Reynolds number. Since we know the velocity, so the formula for Reynolds number when the velocity is given is this, Vd upon mu, okay? So diameter is known, okay, and velocity is also known, and the kinematic viscosity we can get it from the table. So from this we get the Reynolds number comes out to be 3350. Since this Reynolds number is greater than 3000, so we are sure that this is going to be the turbulent flow. So the first answer is that the flow is turbulent. Now, if it is turbulent flow, then the formula was entrance length over diameter is equals to 50. Then it does not depend upon Reynolds number. Then it's a fixed value 50. So if you just multiply 50 by diameter, you're going to get the entrance length comes out to be 0.25 meter. So till 0.25 meter, the flow is developing. There is inviscid region within the pipe cross section. But after 0.25 meter, the inviscid region finishes and the velocity profile becomes fixed. So this is the solution for part A. For the case of the water, again, first we need to find out the Reynolds number, but in the case of the water, we don't have the velocity, we have the mass flow rate. So if we have a situation like this, that mass flow rate is given, then the formula would be 4m dot over pi d mu. Again, m dot is given, diameter is given, and mu we can get it from, or the dynamic viscosity we can get it from the table, or it will be provided to you in the exam within the question itself. So substituting the values, you get the Reynolds number as 1787. Since this value is less than 2000, so we are 100% sure that it's going to be the laminar flow. For the case of laminar flow, the formula is LE by D equals to 0.05 into Reynolds number. That depends upon the Reynolds number. So we just substitute the values of the Reynolds number and diameter. We can get the entrance length region is 0.447 meter. So for the case of the laminar flow, if the water is flowing, we get what is the entrance length, and also for the case of the air, where when it is turbulent flow, we get the entrance length. So that's the solution of this problem. If there is anything within the solution which is not clear to anybody, please feel free to ask. Okay, so let's move over to the next topic. This is about the standard size for pipes. Call it nominal pipe size. Okay. Now, this is an important topic for basic understanding. Suppose if you go to a mechanic or if you go to a plumber, and the plumber sometimes tell you that, okay, we need to get a pipe of 6 inches or 2 inches or 1 inch or half-inch pipe. It does not, what does that inch refers to? Because you know that the pipe is normally have a certain thickness, and based on the thickness of the pipe, you're going to have an outer diameter of the pipe, and then obviously then inner diameter of the pipe. So when a specific size of the pipe is mentioned, what does this mean? Is it the outer diameter or is it the inner diameter? In reality, it is neither the outer diameter nor the inner diameter, but it is the nominal pipe size. And based on the nominal pipe size, there's a specific chart developed, which is actually, which determines that for this specific nominal pipe size, what will be the inner diameter of the pipe and what will be the outer diameter of the pipe, okay? And correspondingly, what will be the thickness of the pipe, okay? So if you look here, this chart, this is the chart for the nominal pipe sizes. If it is said that we have a pipe of nominal pipe size ½ inch, so it does not mean that the inner diameter is ½ inch or the outer diameter is ½ inch. It is the nominal pipe size. Okay, its nominal pipe size is not the inner diameter and also not the outer diameter. But in this case, the outer diameter is 0.84 inches, and the inner diameter depends upon the thickness, wall thickness. Okay, and how do we define the wall thickness? It is defined in terms of the schedule. So, for example, in the market we have a ½ inch pipe of 40 schedule and 80 schedule. So when we say 40 schedule pipe, that means a wall thickness of 0.109. When we say the 80 schedule pipe, that means a wall thickness of 0.147. So corresponding to the wall thickness, you can find out what will be the inner diameter. So outer diameter minus twice the wall thickness, you get the inner diameter. So if the outer diameter was 0.84, the inner diameter, given the wall thickness is this, comes out to be 0.622. Similarly, if the outer diameter is 0.84, given the wall thickness is 0.147, the inner diameter will be 0.546. Okay, so the formula for the case of inner diameter will be outer diameter minus twice the wall thickness. So this will be the formula. So now the point for you to remember is you don't need to memorize that for which nominal pipe size, what will be the outer dia, what will be the inner dia. But point for you to understand is that corresponding to any nominal pipe size, you will have a specific outer diameter, and corresponding to a specific schedule, you can calculate what will be the inner diameter. The second thing is that if the schedule increase, the thickness increase. So when we say schedule 40 and schedule 80, which one will be the thicker pipe? The thicker pipe will be the schedule 85. The schedule 85 pipe will be a pipe which can withstand higher pressures because it is thicker. Okay? It is more stronger. Okay. Similarly, for the case of one nominal pipe size, a 1 inch nominal pipe size, the outer diameter is 1.315. And then again, you have a schedule of 40 schedule, 80 schedule. Corresponding to that, you have wall thicknesses, and then you can find out what is the inner diameter. Similarly, for the case of 2 inch nominal pipe size, 4 inch nominal pipe size, 8 inch nominal pipe size. You can see here from ½ inch till 8 inch, you have 2 schedules available in the market, 40 schedule, 80 schedule. Okay. But after 8 inch nominal pipe size, then let's say we talk about the 14 inch nominal pipe size. You have the 2 schedules. They are not 40 and 80, but rather they are 10 and 40. Okay. In fact, not 2 is we have 4 schedules: 10, 40, 80, 120. Okay. So these are the 4 schedules. Again, 10 schedule will be the most thin pipe, and 120 schedule will be the most thick pipe. In this case, this will be thick. This will be thin. And you can see the thickness here is 0.25 inches, and the thickness here is 1.093 inch. But the other thing to note is that from 14 inch nominal pipe size onwards, the nominal pipe size is actually the outer dia. This was not the case earlier. If it was 8 NPS nominal pipe size, 8 inch nominal pipe size, the outer dia was 8.625. It was not the same as 8. But for the case, once you reach 14 inch nominal pipe size, then onwards from 14 inch, whatever the nominal pipe size is, the outer dia is the same as the nominal pipe size. The inner dia will be definitely less based on how much is the thickness. Okay. So the point for you to memorize is that nominal pipe size is not the inner dia, neither the outer dia. It is a specific pipe size corresponding to which the pipes are available in the market. And the schedule refers to the thickness. The larger the value of the schedule, the larger the thickness. These are the points for you to remember. And another point to remember is that from 14-inch nominal pipe size onwards, the nominal pipe size is actually equal to the outer dia of the pipe. From 14-inch onward, not before that. Okay. So these are some of the things that are important for you to understand or to memorize that could be asked in the short questions. So the schedule, you should know what does the schedule means, what does nominal pipe size means, okay, and that's it. So if there's anything within this, obviously these schedules and these nominal pipe size are the ones which are commercially available in the market. So it's not like that any specific pipe size of any thickness you can get from the market. There are some commercially available sizes and commercially available thicknesses that you can find. And if you want to find a pipe of a specific size of a specific thickness, then you have to follow the commercially available standards. And the commercially available standards are based upon the nominal pipe size and the schedule. So you can go to the market and say that, okay, I need a 4-inch nominal pipe size, schedule 18. Or you can say that I need a 14-inch nominal pipe size, schedule 120. Okay? Or you can say I need a 24-inch nominal pipe size, schedule 10. But you have to, whenever you're purchasing pipe from the market, you have to go for the commercially available ones. And these are the commercially available ones. And this is how you can actually get them from the market. So this is about the standard size of pipes, commercially available ones. And NPS is specified using two values, a nominal pipe size and a schedule. So this is an important point for you to remember. The nominal pipe size determines the outer diameter. For example, pipe with a nominal size of 2-inch have an outer diameter of 2.375 inches. Once the nominal size reaches 14 inches, the nominal size and the outer diameter are equal. That is, a pipe with a nominal size of 24-inch will have an outer diameter of 24-inch. Pipe schedule is related to the thickness of the pipe. This is another point for you to memorize. So what does pipe schedule means? It means the thickness of the wall of the pipe, okay, which in turn is the ability of a pipe to withstand pressure. Thus, pipe schedule correlates with the wall thickness. Okay, so larger the pipe schedule, larger the wall thickness, larger the pressure a pipe can handle. Okay, so each nominal pipe size has many possible schedules that range from schedule 5 to schedule 160. It's neither the unit of length, it's now nor the unit of centimeter. It's basically a specific number, and corresponding to that number, there is a specific chart through which you can find out that what are the diameters, what are the dimensions, what are the thicknesses.
5 to 168, basically each chart will demonstrate.
Yes. Okay. So that's about the standard sizes for pipe, which is the nominal pipe size. Okay. Let's have a break of 5 minutes and then we are going to start the pipe head loss. Okay, the next topic is pipe head loss. When we say about the pipe head loss, it means whatever the loss in the pressure or the energy that occurs as the fluid flows through the pipe. Okay, so the combined total head loss is the pipe head loss plus the component head loss. The component head loss is associated with the flow through devices such as valves, bends, tees. It is sometimes also called as the minor head loss. So normally, in the basic fluid mechanics field, it is referred to as the major head loss and the minor head loss. For the case of pipe head loss, this is associated with fully developed flows in conduits and is caused by shear stresses that act on the flowing fluid. It is sometimes called the major head loss. It is predicted with the Darcy-Weisbach equation. The Darcy-Weisbach equation says that HL, which is the head loss in a pipe, is equals to F L by D V square upon 2G, where F is the friction factor. Okay, so the thing is that you have a pipe and you have the fluid flowing through the pipe. Now there will be friction between the fluid and the pipe. There will be friction between the fluid and the pipe, and because of that friction, there will be losses in the flow. So some of the energy will be lost as the fluid flows through the pipe. Okay, and this loss is termed as head loss, because pressures or energy of the fluid is referred in the fluid mechanics as head. Okay, so whenever we are talking about the pressure loss or energy loss, this is known as head loss. Okay.
Let's say that it was only the positive scenario and this can where we have a component that is actually using the.
No, that's not possible. That's not possible. We can only have losses in the system, but there is no way. Yeah, suppose if it is a pump, then pump is another device. Pump is another, but there cannot be any component which is actually adding energy into the fluid. It's the energy content decreases. Yeah, it is converted from one form to another form. Okay, so the pressure is decreased, velocity is increased, but during this transaction, when the pressure is being decreasing and the velocity is increasing, there is some loss in the overall energy. Okay, so it's not possible. This is basically the second law of thermodynamics, or basic enormity within this within the world, that you do not have any system where you do not have any losses. There will always be, yeah, you can minimize the loss as much as you can, but still there will be losses, whether very small, very little, but they will be there. Okay, so the thing is that whenever the fluid flows through any pipe bend or a pipe T, okay, or there is a specific opening, okay, or the pipe is entering into a smaller pipe, so there is a sudden expansion or sudden contraction. Okay, so whenever there is a specific component, you are going to have loss in energy as the fluid flows through that component. Okay, but that loss is only associated with the fluid flowing through that component, so it is known as the minor loss or component loss. But as the fluid flows throughout the entire pipe, so during the fluid flow through the pipes, there is the viscous effects. There is the viscous effects or the friction between the fluid and the pipe material that causes the losses, and this is known as the major loss. So the losses because of the viscous effects are known as the major losses, and the losses because of a specific component is known as the minor loss. Normally, your pipe system or any fluid piping system is based upon different components and pipes. So you'll have let's say you have a pipe, and then you have a bend, 90-degree bend, then you have another pipe, then you have another 90-degree bend, then you have a T. So it will be composed of major losses and minor losses altogether. Major losses as the fluid flows through a straight pipe. Minor losses as the fluid flows through any specific component. Okay. So whenever you have losses, which is specifically the major loss, so the major loss is actually determined or predicted by the Darcy-Weisbach equation. And the Darcy-Weisbach equation says that the head loss in a pipe, HL, is equals to F, which is the friction factor. Friction factor is important because how much is the roughness of the pipe. If the pipe is too rough, then you will have more losses in energy. Okay, so you have a pipe which is made up of plastic, smooth pipe, and you have a pipe made up of concrete. The concrete, even you make it as much as smooth, still the surface will be very rough. Okay, so the losses of energy as the fluid flows through the concrete pipe will be more than the losses of energy as the fluid flows through a plastic pipe. Suppose if it is a very smooth pipe, let's say a glass pipe. Now, in case of the glass pipe, it is very, very smooth. So the losses will be much more less. It will be there. Eventually, it will be there whether it is any pipe. But higher the losses if the friction factor is high. Lower the losses if the friction factor is less. That depends upon how much is the how smooth is the pipe, or what is the roughness in the pipe. So that's basically F, which is the friction factor. Then what is the length of the pipe? So you have two pipes of equal roughness, but one smaller pipe, one larger pipe. So the larger pipe will have a larger loss, larger head loss. Okay. So you have L, then what is the diameter of the pipe? So larger diameter will have less losses because the head losses are coming because of the friction between the pipe and the fluid. So if the diameter is large, okay, then there is less region compared to how much the fluid is entering into the fluid into the pipe. There is less connection or less contact between the fluid and the pipe itself. So then we have the velocity of the fluid. Okay, so velocity of the fluid is also directly affecting the head loss. Okay, so basically this is the factor F L by D V square upon 2G, and this was predicted by Darcy-Weisbach. That's why it's known as Darcy-Weisbach equation, which actually determines that what will be the head loss in a pipe.
दोनों पाइप्स के अंदर सेम प्रेशर में पानी आ रहा है, बट वन पाइप इज वेरी वेल नीचे की तरफ, एक पाइप इज वेरी ऊपर की तरफ. तो ऑब्वियसली बात है कि इट्स लाइक एक्टिंग अगेंस्ट ग्रेविटी, तो सीधी ओवर रिस्पेक्ट एक दो ज्यादा हो जाएगा एक्टिंग अगेंस्ट ग्रेविटी. तो उस सिनेरियो के अंदर जो जी नेगेटिव है,
No, G will not be negative here, because here this G is not acting independently. It is basically a part of this term, which is the kinematic, or which is the kinetic pressure head. In both the scenarios, there won't be any change in formula because we are talking about the component loss, not the elevation head. Elevation head is different. Head loss is different. Okay. No, if you remember, because I think you missed chapter number 7. In chapter number 7, we developed the energy equation. In energy equation, you had the hydrostatic pressure head. Then you have the elevation head. Then you have the kinetic head. Then you had the pump head. Then you had the turbine head. And then you have the head loss. So if the pipe is going up or pipe is going down, it's going to affect the elevation head. It's not going to affect the head loss. This is only, this is only one component of the entire energy equation that we are focusing right now. And that entire energy equation we developed and we solved multiple problems in chapter number 7. Okay. But now we are focusing ourselves over that one component of that entire equation, which is the head losses. Okay. So the answer to your question, no, it's not going to affect the head loss. It's going to affect the elevation head in the main energy equation. Okay. Okay, so now our objective is to study the stress, shear stress distribution in pipe flow. So if we study the shear stress distribution in pipe flow, okay, and we apply it within the velocity gradient, inside with the velocity gradient over the equation of the shear stress, which is tau equals to mu dv by dy. Okay, we are going to end up into this formula where velocity will be equals to this thing, and correspondingly, it could be said that if we know the velocity in a pipe for the case of the laminar flows, so we can also find out what is the volume flow rate. So volume flow rate is velocity integrated over the entire cross-section area. So the formula for it becomes like this. Now there is a specific flow which is known as Hagen-Poiseuille's flow. Now Hagen-Poiseuille flow is basically what? It is the laminar flow in a round pipe. Okay. So laminar flow in a round pipe is known as Hagen-Poiseuille's flow. Now this is an important point for the short questions or the conceptual question point of view. If it is asked in the exam, what is Hagen-Poiseuille flow? It is laminar flow in a round pipe. Okay. So these are basically the formulas for the Hagen-Poiseuille flow. When applying, when integrating the equation for the Hagen-Poiseuille flow, we comes out the end result comes out to be P1 upon gamma over Z1 equals to P2 upon gamma plus Z2 plus HF. HF is the friction head, or these are the head losses that we are dealing with. Okay. And the formula for the HF comes out to be this 32 mu LV over gamma D squared. Okay. Again, this formula can be proved if you can just substitute the values of velocity profile for the laminar velocity profile in the formula for the head losses. Now, this formula for the case of Hagen-Poiseuille's flow, when we apply it for the laminar flow in a round pipe, the head loss formula comes out to be 32 mu LV over gamma D square, and this is known as Darcy-Weisbach equation. It can be written in the form of Darcy-Weisbach equation. So if we write it in the form of the Darcy-Weisbach equation, the friction factor for the case of laminar flow comes out to be 64 over Reynolds number. So for the case of Hagen-Poiseuille's flow, when it is a laminar flow in a round pipe, the friction factor of the Darcy-Weisbach equation comes out to be 64 over Reynolds number. Again, these formulas will be provided to you in the exam. You don't have to memorize them. But there are a few things that you have to remember. The first thing is that what is a Hagen-Poiseuille flow? Hagen-Poiseuille flow is a laminar flow in a round pipe. The second thing is that what is Darcy-Weisbach equation? This is the general format of the Darcy-Weisbach equation. What are the terms within this equation? F is the friction factor, L is the length, P is the diameter, V is the velocity. Okay, and what will be the friction factor of the Darcy-Weisbach equation for the Hagen-Poiseuille's flow? It comes out to be 64 over Reynolds number. Okay. So these are some of the things that you should understand. Okay, so now let's apply it in a numerical here. Okay, we have an oil with a specific gravity of 0.85 with a kinematic viscosity of 6 into 10 to the power minus 4 meters square per second, flows in a 15 centimeter pipe at a rate of 0.02 meter cube per second. What is the head loss per 100 meter length of pipe? Okay, so the thing is that we have a pipe here. It's a straight pipe. Okay, and the pipe length we are talking about is 100 meter. Okay, so let's say this is 100 meter length. Okay, diameter of the pipe is this. This is the diameter of the pipe. Okay, the oil has a specific gravity given, kinematic viscosity given. Okay, and the volume flow rate is given, Q. Okay, we need to find out how much is the head loss within the pipe, which is basically HL, or it is written as HF. Why it is written as HL and HF? HL is the head loss, HF is the friction loss, because head loss is basically because of the friction effect, which is because of the viscous effect. So it's written like both ways. So the first thing is that we need to find out if it is a laminar flow or a turbulent flow. Now, how do we determine it? We need to find out by using it by using the Reynolds number. Now, for the case of the Reynolds number, what we can do is that since we know what is the volume flow rate, so we can use the volume flow rate to find out the velocity. So the formula for the case of volume flow rate is Q is equals to AV. Since we know Q and we know A, Q is given directly, and since we know the diameter, we can find out what is the cross-section area. So corresponding to Q and A, we can find out what is the velocity. Q is the volume flow rate. So knowing the volume flow rate and the cross-section area, we can find out the velocity. Knowing the velocity and diameter and kinematic viscosity, we can find out what is the Reynolds number. So substituting the values, we can find out the Reynolds number is 283. Since the Reynolds number is less than 2000, so we know that this will be laminar flow. So for the case of laminar flow, we can find out head loss using the Darcy-Weisbach equation for the case of the Hagen-Poiseuille flow. So it will be HF equals to 32 mu LV over gamma D squared. Okay. Now in this formula, mu is something which is the dynamic viscosity that we know. Okay. For the case of the fluid, length is 100 meter. This is also known. Velocity we have already calculated. Diameter is known. Gamma is known. Why gamma is known? Because we know the specific gravity. So if you know the specific gravity, you can find out what is the specific weight. So correspondingly, if you just substitute all these values, you can find out the head loss comes out to be 9.83. The other way around is that since we know that it is laminar flow, so we can directly find out what is the friction factor. Because for the case of Darcy-Weisbach equation, if you want to use, the friction factor will be 64 over Reynolds number. Substitute the value of Reynolds number into this formula, you can find out the friction factor. Once you have the friction factor, you can substitute it into Darcy-Weisbach equation. Knowing the length, diameter, and velocity, we can find out how much is the head loss. It will be the same as you get from here. So that is the solution to this problem. If there is anything within the solution to the problem which is not clear, so you can ask. That was about for the case of laminar flows. Now let's say that we are talking about the turbulent flows. Okay. So for the case of turbulent flow, now if we want to find out head loss, we cannot use this formula directly. This formula is only for the laminar flows. You cannot use this formula for the case of turbulent flow. Okay. However, the general formula, the general format remains same. The general format of the Darcy-Weisbach equation remains same for the case of head loss. Okay. So this formula is the general format, and general format you can use it. But the point is that even if you want to use the general format, first thing you need to know is you need to know what is the friction factor. So if you can find out the friction factor, then we can use the general format, and then you can use this formula for the case of the turbulent flows as well. So now let's discuss a little about turbulent flows. In case of turbulent flows, what happens is that the flow velocity, the flow profile, velocity profile is also going to be changed. The flow is composed of two parts. You have an average flow, and over the average flow, you have superimposed disturbances. Okay. So obviously disturbances are something which cannot be predicted at all, but the average flow is something which can be predicted. So based on the average flows in case of the turbulent flow analysis, we do the flow prediction analysis. First of all, for the case of the laminar flow, the velocity profile would be a parabola. But for the case of the turbulent flow, it's like a parabola which is hammered. So if you have a parabola and you hammer it on this side, so it will become a little flattened. Okay. So it's a hammered parabola, you can say, for the case of the turbulent flow, the velocity profile will be. So this is for the case of the laminar flow, a perfect parabola. But for the case of the turbulent flow, it's like hammered a little at the edge. So it is going to be flat out a little in the center. Anyways, we can use the Darcy-Weisbach equation to find out the head loss for the case of turbulent flows. But in order to do that, we need to find out what is the friction factor. Now, for finding the friction factor for the case of the turbulent flows, we have to use the Moody diagram. Now, Moody diagram is the most important diagram here, which is going to help us out find out the friction factor for the case of turbulent flows. So if we have the friction factor for the case of turbulent flows, then we can use this Darcy-Weisbach equation to actually find out the head loss. Now let's try to learn and understand this Moody diagram step by step. This is actually looks like a complicated diagram, and it is in reality a little complicated diagram, but it's an important diagram for understanding or for solving the problems for flowing conduits, especially for the case of turbulent flow. And in numeric and in practice, more than 80% of the cases you have the turbulent flows. So this is a very significant diagram for finding out the friction factors. First of all, what is the objective of Moody diagram? The main objective of Moody diagram is to find out this friction factor. To find out friction factor. Okay, this is the main objective of the Moody diagram. Okay, and why do we need to find F? Because we need to find how much is the head loss. Head loss we can find using this equation, but in this equation F is needed. So if we have F, you can find head loss. If you have head loss, you can find out what are the component losses, as well as you can find out what are the pipe head losses. You can find out the major losses, you can find out the minor losses. So you can find out the overall losses in the pipe system if you know the head losses. But for finding the head loss, you need to know what is F. And for the case of turbulent flows, for finding F, you need to use the Moody diagram. So this is the main thing. That's why F here is on the y-axis. Now, what do we need to find F in this Moody diagram? On x-axis, we have Reynolds number. So if we know the Reynolds number, corresponding to the Reynolds number, we can go on the x-axis and then move up and find out a specific curve. Now, if you look here in this figure, okay, x-axis is clear. On x-axis, you have the Reynolds number. Y-axis is clear. You have the friction factor that we need to find. What is there in the center? In the center, you have a lot of curves here. Okay, and these curves are basically for relative roughness. You see here? This is relative roughness. Relative roughness is Ks by D. D is the diameter. Okay, so you have a pipe. Let's say you have a pipe. Okay, and the fluid is moving within the pipe. But if you look from the microscope, the pipe is not actually smooth. And if you look deep, you'll find out that the surface of the pipe is like this. It's not perfectly smooth. There is roughness. Okay, and if you further go deep, you can find out that how much is this? How much is this up and down? So this up and down is basically the roughness of the pipe. Obviously, if it is a pipe made up of concrete, or the pipe made up of wood, or the pipe made up of brass, or the pipe made up of steel, or the pipe made up of plastic, or a pipe made up of glass, each material have its own roughness. Okay, so this Ks is basically the pipe roughness. So Ks by D is basically the dimensionless value of pipe roughness. We call it relative roughness. Diameter is in the unit of meter, and Ks is the roughness. How much is up and down? This is also the unit of length. So unit of length divided by unit of length, it's dimensionless. So relative roughness is dimensionless parameter. Okay. So here we have in the center, you see here all these dark blue lines. All these dark blue lines are basically the relative roughness lines. So if we know what is the specific relative roughness for the pipe that we are considering, that the that is there in consideration, we can actually reach to that specific relative roughness curve, and then we can find out what is the friction factor. Okay. So the values of these Ks by D are mentioned here, which is 0.00001, and these values are increasing, and the maximum value here is 0.05. Okay. So suppose that you have a case. Okay. We are going to come over to the solution here, but okay. Anyways, this here, the dark blue lines are the relative roughness lines. Now, if you look here deeply, let's look at the x-axis. Now, if you look here at the x-axis, the x-axis is not linear. It's basically log. So you see here, this is 10 to the power 4, means 10,000. Then this is 2 into 10 to the power 4, means 20,000. Then this will be 40,000, 60,000, 80,000, 100,000. 10 to the power 5 is 100,000. So this is not linear. This is log. Okay, then so the values are here like this: 10 to the power 4, 10 to the power 5, 10 to the power 6. Okay, and all the x-axis is mentioned in the form of 10 raised to the power. Okay, so this is known as the log diagram, because on the x-axis the values are not there linear. The values are in the form of logarithmic. Okay, so if the value is here 10 to the power 4, that means 1 into 10 to the power 4. Then this is 2. And even if you look here, between 1 to 2, the difference is this much. Between 4 to 6, the difference is smaller. Between 6 to 8, the difference is even much smaller. 8 to 10, the difference is even much smaller. Because this is a log table. This is a log figure. Okay. So you need to know how to read the log diagram rather than a linear diagram. Okay. So here Reynolds numbers are mentioned in the form of a log, as well as the friction factor is also mentioned in the form of a log. So you can see here between 0.025 to 0.03, the difference is this much. Then 0.03 to 0.04, then 0.05, onwards like this. So suppose if you know a specific Reynolds number and you know what is the specific relative roughness, what will happen is that you are going to come over to the x-axis, find out that specific Reynolds number, then move towards a specific curve for the relative roughness, intersect that specific curve, and then move on the y-axis to find out what is the friction factor at that point. Okay, when we look at the top x-axis, you don't have the Reynolds number but we have another term here, which is Reynolds number multiplied by friction factor power half, which is equals to d power 3 by 2, which is the diameter power 3 by 2 divided by kinematic viscosity multiplied by 2g hf divided by L power half. Okay, so this is the terminology. If you find out this terminology, so if you look here, the dark black lines, which are basically a little inclined, a little tilted, these are the values of this term. So if we are able to figure out this term, then we can use these dark black lines to intercept. What we need to find is, we need to find the friction factor. We can find out the friction factor if we actually find out a specific point on this graph. Corresponding to that, we can then find out what is the friction factor. Now, in order to find a specific point in the graph, we need to intercept between 2 points. Okay, either you use the bottom x-axis and the curve, or you use the top x-axis and the curve. But if you use the top x-axis, then you have to use the dark black lines rather than the regular lines, regular grid lines. Okay. Now, relative roughness, if you see here, the dark blue lines are the relative roughness. The relative roughness at the top is the highest. Then as you keep on moving down, the relative roughness is dropping. And the last line is the one for which the relative roughness is almost zero, and we call it as a smooth pipe. So if we have a situation in the problem where it is mentioned that the pipe is a smooth, that means you have to use the last curve here, which is for the case of the smooth pipe. Now this is all for the turbulent region. This is all for the turbulent region, because if you see here, the turbulent flow becomes turbulent when the Reynolds number becomes greater than 3000. Less than 2000, it's laminar. Okay, so 3000 means 3 into 10 to the power 3. Okay, so here we have 10 to the power 3. This is 2 into 10 to the power 3. So 3 into 10 to the power 3 will be somewhere here. So this is the point below which here we have the transition region. This is the laminar region, and this region, this is all turbulent. Okay. So laminar region is below 2 into 10 to the power 3. That means this point. So here we have laminar, here we have turbulent, and this small region is basically this small region is the transition region. But as I told you, for the course of this study, transition region is something that we are not considering in our analysis. So either it will be the laminar flow or the turbulent flow that we will consider. So this is how we read the Moody chart. If anybody have any question regarding the Moody chart, you can ask. Otherwise, when we will be solving the problem, then we will eventually be looking at how to read values from the Moody chart. So we have different kind of problems through which we can actually solve problems and find values from the Moody chart. So let's move towards one by one how to solve these problems. Let's have a break of 5 minutes and then we will start back. Okay, so now let's see an associated problem. Water at 20 degrees centigrade flows at a rate of 0.05 meter cube per second in a 20 centimeter asphalted cast iron pipe. What is the head loss per kilometer of pipe? So we have a situation here that water is flowing through a pipe and the flow rate Q is 0.05 meter cube per second in a 20 centimeter, so that will be the diameter, asphalted cast iron pipe. It's mentioned it is asphalted cast iron pipe. Why? Because for this specific pipe, we can find out that what is the relative roughness. So Ks over D. So we need to find out that what is the head loss per kilometer of the pipe. So we need to find out what is the HL per kilometer of the pipe, means for the pipe length we are considering as 1000 meter. Okay. So we have a situation here like this, that let's say the length is 1000 meter, water 20 degrees centigrade, flowing at a flow rate of 0.05 meter cube per second. Diameter of the pipe is 0.2 meter. And this pipe is made up of asphalted cast iron. Since we know it is water and we know the temperature of the water, so we can find out what is the kinematic viscosity of the water, or it will be provided to you in the exam in the form of a table or directly within the problem statement. So it's 1 into 10 to the power minus 6 meters square per second. Since we know that it is asphalted cast iron pipe, so for this case, the Ks will be provided to you in the exam. So Ks is basically the roughness of the pipe. Okay, so that will be provided to you in the exam, that what is the roughness of the pipe. So in order to solve this, we need to find HL. So first we need to see whether it is a laminar flow or a turbulent flow. Okay, so we know the volume flow rate, so we can find out what is the velocity. There's a formula. Since we know Q and we know the diameter, we know the cross-section area. So corresponding to that, we can find out that the velocity is 1.59 meter per second. And using the velocity in the formula for the Reynolds number, Vd upon mu, we know what is mu. Kinematic viscosity, we know what is diameter, we know what is the velocity since it is already calculated here. So we can find out how much is the Reynolds number. So Reynolds number is 3.18 into 10 to the power 5. Since this value is greater than 3000, so we know that this is the turbulent flow. If it is turbulent flow, we cannot use Hagen-Poiseuille's formula. So this formula for HL, we cannot use because this is not a laminar flow. This formula was only for laminar flow. Now we have to use the Darcy-Weisbach equation, and we have to use for the case of turbulent flow. So we have to use the Moody chart. Now, in case of the Moody chart, on the x-axis, you have the Reynolds number. So Reynolds number is something that we have already determined, 3.18 10 to the power 5. Okay. Then the next thing is that we have to intercept it with a specific curve of relative roughness. Now, since we know that it is asphalted cast iron pipe for which the roughness is provided as 0.12 millimeter, so we can find out what is the relative roughness. Relative roughness will be Ks by diameter. Since we know the diameter and we know the roughness, so the relative roughness is 0.0006. Now what we can do is that we can go into the Moody chart and we can find out what is the friction factor. Okay, so we have Ks by D as 0.0006, and we have Reynolds number 3.18 10 to the power 5. So let's go into the Moody chart. This is the Moody chart. So let's try to find out where is Ks by D 0.0006. Okay, so this is 0.0006. So which curve are we looking? This curve that we are looking. This is the curve that we are looking. This is Ks by D 0.0006. Now, Reynolds number was how much? It was 3.18 10 to the power 5. So now let's try to figure out where it is. We're talking about 10 to the power 5. So this is 10 to the power 5. This will be 1 into 10 to the power 5, 2 into 10 to the power 5, 3 into 10 to the power 5. So 3.18 would be somewhere here. Okay, so that will be, so let me draw a line. So so this is 2, this will be 3, 3.18 would be somewhere here. So now I want to draw a line. This is the line drawn. Okay, and this line is intercepting at this point. This is my point of interception. Okay, now once I know the point of interception of Ks by T D with the Reynolds number, so I can follow on horizontally to figure out that what will be the friction factor. So horizontally it will be here. So the friction factor will be so this will be the friction factor here. So this is 0.02, but it is one line below 0.02, the 0.015, 0.016, 0.017, 0.018, 0.019. So friction factor comes out to be 0.019. Okay, so this is how we have done. We have done by using the Moody chart. So first we find out what is the Ks by D. We'd find out what is the Reynolds number, intercept the two lines, and at the point of interception, go horizontally and find out what is the friction factor. Okay, so now we have the friction factor. The dark black lines. Okay, when we have a situation where we don't have the Reynolds number directly, then you cannot use the bottom x-axis. For the bottom x-axis, you need to have the Reynolds number. If the Reynolds number is not there directly with us, then we have to use the top. Okay. So here in this case, now we know what is the friction factor. So this is a problem. So the friction factor comes out to be 0.019. So now this is the Darcy-Weisbach equation. In this Darcy-Weisbach equation, we are going to use the value of the friction factor. Length is known, diameter is known, velocity is known. Substitute all the values. You're going to find out how much is the head loss. So the head loss comes out to be 12.2 meter. So this is how we have solved for the case of turbulent flow. For the case of turbulent flow, you need Moody chart because you need to find friction factor. Without finding friction factor, you cannot find what is the head loss. Bottom line. Okay. If it was laminar flow, there was a direct formula that came out using the Huygens-Poiseuille's formulation. Okay, so you do not need the chart. Yeah, in the Moody chart, you also have the region for the laminar flow. You can also use the Moody chart for the laminar flow as well. This is the region for laminar flow. Okay, but in case if you don't want to use the chart, it was possible. But for the case of the for the case of the turbulent flows, you have to use the Moody chart. Or there is a direct formula as well, but this is quite a complicated formula for finding out F. This is known as the Colebrook-White correlation. So Colebrook-White actually developed a correlation which actually is a good approximation for the case of Moody chart. So that's the solution of this problem. If there is anything within the solution of this problem which is not clear, please feel free to ask. Okay, let's move over to the next problem. The head loss per kilometer of 20 centimeter asphalted cast iron pipe is 12.2 meter. What is the flow rate of water through the pipe? Now, in this case, the head loss is given. This is HL, or you can say HF. This is given. Head loss is given per kilometer of pipe. So kilometer means L is 1000 meter. That's the same problem. Of 20 centimeter asphalted cast iron pipe. So again, diameter is given. And it is asphalted cast iron pipe, so Ks is known. If Ks is known, so you can find what is Ks by D. Since the diameter is the same as the previous problem, and it is the same asphalted cast iron pipe, so Ks by D will again come out to be 0.0006, as we did in the last problem. Now, in this case, try to figure out what are given. Head loss is given, length is given, diameter is given, Ks by D is given. And what do we need to find out? We need to find out the flow rate. Q. This is what we need to find out. Okay. Now, the basic formula for flow rate is what? Formula for flow rate is Q is equals to AV. A is known because diameter is known, but we don't know the velocity. If we don't know the velocity, we don't know the Reynolds number. Correspondingly, we don't know the Reynolds number. Okay. So this is the situation where now we need to find out the velocity. So how can we find out the velocity? If we somehow find out the Reynolds number. If we somehow find out the Reynolds number, then the formula for Reynolds number is what? Formula for Reynolds number is Or you can see here as well. Formula for head loss is this. Because the head loss is known, length is known, diameter is known, friction factor is not known. In this problem, friction factor is not known, velocity is not known. Okay. So somehow, if we know the friction factor, then we can use this formula to find out the velocity. And if we know the velocity, then we can use it here to find out Q. So we need to go back way around. Okay. So so now if you look at the Moody chart, one thing is very clear in this Moody chart, we don't know the Reynolds number. Okay. But here, this is the term. We can find this term. This term is what? It is diameter, kinematic viscosity, because head loss is given, HF is given, and G is the acceleration due to gravity, length is known. So we can, if we substitute the values, we can find out this term. Okay. So we're going to go back into the problem and see if we substitute all these values. So this is the term here. If we substitute all the values, we're going to come up with the answer that this term is 4.38 into 10 to the power 4. So now we are going to use the top x-axis. So the approach would be what? Approach would be find out this term to find out friction factor. And then once we have the friction factor, use the Darcy-Weisbach equation to find out velocity. And then once we have velocity, find out Q. Okay. So we are using this term. So this term it will be 4.38 into 10 to the power 4. Okay. So we're going to go back into the diagram, 4.38 into 10 to the power 4. So it's 10 to the power 4. This is 10 to the power 4. So that's 1 into 10 to the power 4, 2 into 10 to the power 4, 4 into 10 to the power 4, and it is 4.38. Okay, so if I draw it, it will be somewhere here. So from this, I'm going to draw a parallel line, and I have to intercept the same relative reference line. So that's 4.38 into 10 to the power 4. Okay, and again, the point of interception would be here. So correspondingly, if I go on the horizontally, I can find out what is the friction factor. Okay, so the friction factor would come out to be same because it is the same problem that we are dealing with. It's just the values are changed so that the given is changed so that we can use the other format of the Moody diagram. So here, once we substitute the values, F value again comes out to be 0.019. Once we have this F value as 0.019, then we can substitute the value of F here. And we can find out what is the velocity. The velocity is determined. And then corresponding to the velocity, if we substitute it into the formula for volume flow rate, we can find out how much is the volume flow rate. So this is the second problem, which is actually showing you how you can use the Moody chart. Okay, if the velocity is not directly given, and if the head loss is given, so if the velocity is given, use the Reynolds number to find out friction factor. If head loss is given, then we can also use that head loss using the top x-axis to find out what is the friction factor. Okay, and eventually finding out what is the velocity. Okay, we can have another case here, the same problem, but this is these cases, the example 10.5 and then example 10.6. These are the cases where iteration is required, because we have to start with a guess value, solve the problem, then solve it again, and then keep on solving it until the problem converges to a single solution. So, but because here we have iteration needed, so I'm not going to go through it myself with you guys, but the solution is here. I want you to go through it yourself, okay? And look at the solution. Obviously, since the iteration is required, so this kind of problem I cannot give in the exam. But I can ask you in general terms that what is the reason for finding for doing the iterations, okay? And how do you find out, how do you determine that the problem is converged to a right solution? Okay, so this is something that I want you to go through yourself. This is example 10.5 and example 10.6. So that was about the major head losses. So the topic of the major head losses is complete. Now we are going to move towards the minor head losses, the next topic. But let's have a break of 5 minutes and then we will start. Okay, after studying the topic for the case of major head losses, now let's move over to the topic of minor head losses. The minor head losses are also known as component losses. These are actually the ones occurring at the components. For example, valves, elbows, enlargements, contractions, inlets, outlets, bends, branches, or any fittings. So for the case of the minor head losses, we have the loss coefficient K. We determine the loss coefficient K and then we apply it into the basic formulation for the head loss, which is HL equals to KB square upon 2G. Okay, so if we know the value of K for that specific minor head loss, we can find out what is the head loss. What is a minor head loss? Okay. So this K is basically what? It is the ratio of pressure drop due to component to the kinetic or dynamic pressure within the flow. Since it is the ratio of two pressures, so the actual unit of K will be, it's a dimensionless quantity. It will not be there, since it is a ratio of two pressures. So suppose if we have a situation here, we have a sharp-edged entrance. So that means you have a pipe connected to a specific flow entrance, and this pipe connection is sharp. Okay, so it's a pointed edge at the two ends. So what happens is that in generally what happens that the fluid actually try to enter into the pipe, and although pipe has a specific diameter, but because of the entrance flow projection of the fluid, okay, so all the fluid is actually accumulated in a central region. So the effective diameter of the pipe inlet is actually reduced because you have a specific region of flow circulation at the top and the bottom of the pipe. So the effective entrance of the pipe is reduced, and this effective entrance is known as vena contracta. What is vena contracta? Because if you have a pipe and this pipe is connected to a specific tank, the fluid trying to enter into the pipe has to follow a specific trajectory. Okay, that specific trajectory causes the effective diameter of the pipe at the entrance to become small, because we get some flow circulation region at the top and the bottom. Okay, so around the periphery of the pipe, we have the flow circulation region, and the effective diameter of the pipe becomes less than the actual diameter of the pipe. Okay, and so this decrease in the effective diameter of the pipe is known as vena contracta. So the smaller diameter of the pipe that we have the effective diameter of the pipe is known as the vena contracta. Even though as the flow proceeds, it passes away from the flow circulation region, and then the effective diameter becomes again equal to the actual pipe diameter. Okay, so once the fluid passes through this region, and then we have the effective diameter equal to the actual diameter of the pipe. But only in this region, the effective diameter is reduced because of the flow circulation region. Anyways, whenever you have sharp-edged entrance, so there will be some losses at this point, at the entrance point. There will be some losses, which is known as the head loss. But this head loss is occurring at this specific location only, so it is known as minor head loss or component head loss. So the minor head loss, sometimes also written as HM because it is minor. So minor head loss for this case will be 0.5 into V square upon 2G. Whatever the velocity in the pipe, divide by 2G, multiply by 0.5. Okay, so that will be the formula if it is the sharp edge entrance. The other cases is that suppose if it is not if it is not a sharp edge entrance, then that means you have a specific curvature. If you have a specific curvature, obviously then the minor head losses will become smaller. Okay, so the largest will be for the case if the curvature here is 0, which is R by D equals 0, which is the sharp edge, so K value is 0.5. But if there is a specific curvature, so larger the curvature, smaller the value of K. And smaller the value of K, smaller the HM. So the minor losses will become smaller if you have a bigger curvature. So corresponding to what is the value of R by D, R is the radius of curvature, D is the diameter of the pipe, we can have the loss coefficients for this entrance. Then we have other cases as well. This is again the pipe entrance case. Okay, so HL is equals to K entrance V square upon 2G. Depending upon what is the value of R by D, we will have the value of K entrance. Okay. Then we have for the case of contraction. So suppose if I have a bigger pipe and the bigger pipe is the flow is contracted into a smaller pipe. Okay. So we can find out that what is the angle of contraction. Okay, so angle of contraction, how do we represent the angle of contraction? If we join the 2 points here, so this theta is the angle of contraction. So based upon what is the angle of contraction and what is the diameter of the bigger pipe and what is the diameter of the smaller pipe, okay, we can find out what is the loss coefficient for the minor head losses, Kc, for the case of contraction. Okay, so based upon what is D2 by D1, okay, and what is the angle of contraction? If the angle of contraction is 60 degree, then these are the values of Kc. If the angle of contraction is 180 degree, okay, then these are the values. Okay. Similarly, we can have the case of expansion. So you have a smaller pipe, and that smaller pipe is actually connected to a bigger pipe. So, but what is the angle of expansion? So angle of expansion again will be like this. You have one this line, other this line, the 2 points of intersection is going to give us a specific angle between them, and that will be the angle of expansion. So the angle of expansion, if we know what is the angle of expansion and if we know what is diameter D1 and D2, we know the ratio D1 by D2. So corresponding to that, we can find out what is the loss coefficient. Okay, for the case of expansion. So this is for the case of pipe entrance, this is for the case of pipe contraction, this is for the case of pipe expansion. Then we can also have for the case of 90-degree miter bend. Miter bend is one when you don't have any pipe curvature. So you have one pipe and you have another pipe, and this is basically an edge, sharp edge. Okay, so you don't have any curvature. Okay, so that is known as the miter bend. So if it is a 90-degree miter bend with veins or without veins, these are the loss coefficients. If we have a smooth bend is the one when you have a specific curvature. So what is the radius of curvature and what is the diameter of pipe? Based on that, you have the R by D ratio. If you know the R by D ratio, you can find out what will be for the case of this bend, 90-degree bend. What will be the loss coefficient for it? Okay, if we have threaded pipings, pipe fittings, if we have a globe valve, if we have an angle valve, okay, so loss coefficients are provided. If we have a sudden expansion case, the pipe suddenly expanded into a bigger pipe. Okay, so for this case, the minor head loss will be V1 minus V2 square upon 2G provided. If we have a gradual expansion, this is again for the case of expansion similar as we did before. If we have a pipe discharge into a large tank, then in that case, K will be equals to 1. So it is just HM equals to V square upon 2G. So these are some of the specific cases provided to you. Obviously, the tables will be provided to you for those specific cases if they are required to be solved in the examples, in the numericals. So general format is this: KL V2 square upon 2G. If you have a globe valve, angle valve, gate valve, return bend, standard T, 90-degree elbow, 45-degree elbow, we have the specific values of K. So combined head loss, whenever you have a piping system, so a piping system will composed of large pipes and then you'll have components. Okay, so one pipe may be connected to a bend, connected to another pipe, then you might have a valve, then you might have another pipe. So like this. So it will be composed of multiple pipes and multiple connections. So wherever you have a specific pipe, so you'll have a pipe head loss associated with it. And wherever you have a specific component, so you'll have a component head loss. So combining the component head loss with the pipe head loss, we have the combined total head loss of the piping system. Okay, so pipe head loss are basically the major losses. So these are the major losses, and the component head losses are basically the minor losses. So the combined total head loss is a combination of the major and the minor losses. For the case of the major losses, we have to use the Darcy-Weisbach correlation. Okay, so this is the Darcy-Weisbach correlation, and we have to use it for each and every pipe length. So that's why it is the summation of all the pipes. Then we have to also add the summation for all the components to find out what is the head losses for the minor head losses. Okay, so it will be the same formulation KV square upon 2G. So this will be the formula for the combined head loss for the entire piping system. So now let's have a problem associated with it. If oil with a viscosity of 4 into 10 to the power minus 5 meters square per second and specific gravity of 0.9 flows from the upper to the lower reservoir at a rate of 0.028 meter cube per second. So we have a specific gravity, we have the kinematic viscosity provided for the case of the oil, and the flow rate Q is provided in the 15 centimeter smooth pipe. So this is a 15 centimeter pipe, so that's the diameter of the pipe, and it is a smooth pipe. The word smooth pipe is very important because when you will be using the Moody diagram, so in the Moody diagram, you have a specific curve, the most bottom curve, dark blue bottom curve is basically the smooth pipe curve, and it's also written there, smooth pipe. Okay, so what is the elevation of the oil surface in the upper reservoir? This is what we need to find out. So you have a situation like this. You have two reservoirs. You have reservoir 1 and you have reservoir 2. Between the two reservoirs, you have a piping attached. Piping attached is like this. You have a 60-meter pipe. Then you have a bend. Then you have a 7-meter pipe. Then you have another bend. Then you have 130-meter pipe, and then it is connected to the second reservoir. The second reservoir top elevation is 130 meter. The first reservoir elevation is unknown that we need to find out. So we need to find out how much should be this, how much should be the elevation in this reservoir if the flow rate is 0.028 meter cube per second in the pipe. Okay, so for this flow rate of for this flow rate, how much should be the elevation in the first tank? So let's have a small break of Azan. Okay, so we need to find out what should be the elevation of the fluid in this reservoir. Okay, so in order to solve the problem, we have to move towards the formulation that we developed or that we studied in chapter number 7, the energy equation, using the energy principle. Okay, so what we can do is that between point 1 and point 2, we can apply the energy equation for the fluid flow systems. So if you apply the energy equation, this will be the energy equation. P1 upon gamma plus alpha 1 V1 squared upon 2G plus Z1 plus HP equals to P2 upon gamma plus alpha 2 V2 squared upon 2G plus Z2 plus HT plus HL. First of all, we don't have any pump. Since we don't have any pump, so HP is 0. We don't have any turbine, so HT is also 0. Okay, between point 1 and point 2, point 1 is the free surface inside the reservoir. So the velocity will be considered very small compared to the velocity in the pipe. So we can ignore the velocity V1. Similarly, at point 2, it is also the top of the tank surface. Okay, so the velocity at this point will also be very small compared to the velocity in the pipe. So we will consider V1 and V2 also 0. And since they both are open to atmosphere, so the gauge pressures will also be 0. Okay, so let's come here. So the velocity V1 will also be considered 0. Velocity V2 will be considered 0. Gauge pressure P1 will be 0. Gauge pressure P2 will be 0. So our energy equation becomes what? Z1 equals to Z2 plus HL. All of the terms become 0. So this becomes our energy equation. Okay. Now Z2 elevation is known. This is known in the question, right? So elevation Z2 is 130 meter. Z1 elevation we need to find out. So this is we need to find out. Now we can find Z1 if we know what is HL. What are the head losses in the piping system? Now the head losses in the piping system will be because of the straight pipes. That will be the major head losses. And then you have components. You have an entrance here. You have a bend, another here. Then you have another bend here. Then you have an exit. So you have 4 points where you'll have the minor losses. And then you have a straight pipe where you'll have the major losses. And all these losses together is going to make the head loss. So we have to now find out the combined head loss, which will be HL. If we substitute into the formula of HL, into the formula of energy equation that we use, we can find out what is the elevation Z1 that we need to find out. Okay. So this was chapter 7. And finding HL is this chapter, chapter 10, that you are studying right now. Okay. So now let's come over to find HL. This is the formula for finding HL. You will have for the case of pipes and for the case of components. For the case of pipes, it is again, we'll have F, L by D. We can find out what is the length. So total length is what? You see here 60 meter, 7 meter, 130 meter. So 60 plus 130, that's 190, and plus 7, 197. So straight pipe length is 197. Yes. The formula sheet, like I provided in the mid-exam, this formula sheet is basically from the textbook itself. Okay, the same formula sheet will be provided. Okay. So if there are any complicated formulas which I have mentioned during the lecture, that this formula will be provided in the exam, that will also be provided. So suppose if there is a specific formula which is not there in that formula sheet, and that formula sheet is from the textbook. If you go in the textbook, at the bottom of the textbook, you have appendices, and then there's formula sheet also. So same formula sheet I will provide. Okay, but if there is a formula which is not there in that formula sheet, but I have mentioned in the lecture that, okay, this formula I will provide in the exam, then I will separately provide that formula as well. But suppose if there is a formula which is not there in the sheet, and I have also not said in the lecture that I will provide it in the exam, then that formula needs to be memorized. So for this, you need to watch the lecture or remember what you have gone through the lecture. Okay. So there has to be some motivation for you to watch the lecture. Okay. Anyways. So we have this formula, okay, HL equals to. Now, what we can do is that we can remove the summation sign here because rest of the things would remain the same. The only length, because we have three different lengths, we can add them together. So we'll have just one formula for the case of the pipe length, for the case of the major losses. For the case of the minor losses, we have now components. We have 4 components here, as shown here. We have one entrance, one bend 90 degree, another bend 90 degree, and then exit. So you have an entrance, an exit, and 2 bends 90 degree. Okay, so we can write it here like this. So these are for the case of 2 bends. So you'll have the loss coefficient for the case of bend. Then you'll have for the case of entrance. Then you'll have for the case of exit. For the case of exit, it was shown previously that for the case of exit, loss coefficient is 1. Okay, so for this, we already know that for the case of exit, it's basically 1 loss coefficient. But for the case of the entrances, we can actually determine for the case of entrance and for the case of the bends. Okay. Okay, so have a look here for the case of, yeah. For the case of exit, the loss coefficient is 1. Okay. Now for the case of entrance, it is considered a sharp edge entrance because the radius is not mentioned at the point of entrance. So it is 0.5. Okay. Yes, for the case of entrance, we will now consider it as 0.5. Okay. Now for the case of bend. Okay. Now bend is there. If you look here, it is mentioned for the case of bends that R by D is 2. R by D is 2. So now let's see 90 degree bend. This is a 90 degree smooth bend. 90 degree smooth bend. R by D is 2. 0.19, right? So you can see here. Okay. And here the length is 197. How it is 197? Because it is 60 plus 7 plus 130. That's 197. That's the total length of the pipe. 60 length is here, then 7 length, then 130 meter length. So total length of the pipe. Okay. So that's for the case of the major losses. You have length as 197. Okay. And this formula you have, it is FL by D. Okay. So diameter is known, it is 0.15 given in the question. Okay. Now friction factor. You can use this Swami-Jain equation to find out the friction factor, or you can use the Moody chart. Okay. So suppose if you want to use the Moody chart, then we have to first find out what is the Reynolds number. Okay. So we know what is Q. If we know Q and we know the diameter, we can find out what is the velocity. Knowing the velocity, we can find out the Reynolds number. Reynolds number will be VD upon mu, velocity known, diameter known, kinematic viscosity known, we can find out the Reynolds number. Reynolds number is 5.93 into 10 to the power 3, right? This is the case for the smooth pipe. So now let's use the Moody chart. Okay, 5.93 10 to the power 3 is the Reynolds number. So let's go back. So that was the Moody chart here. Smooth pipe. The last curve is for the smooth pipe. Okay. So now we need 5.93 into 10 to the power 3, right? So this is 10 to the power 3, 1 into 10 to the power 3, 2 into 10 to the power 3, 4 into 10 to the power 3. This is 6 into 10 to the power 3. So 5.93 will be very close to 6. Okay. So let's say here it is 5.93. Okay. So we have draw a line, sketch it to the very last line, which is a smooth pipe. Okay, and then somewhere here, right? Point of intersection will come here somewhere here. 0.03, 0.031, 0.032, 0.033. Between 0.032 or 0.033, we'll have it. Okay, so if you look here, so we're getting it's 0.036 by using the they did not use Moody chart, they use Swamy-Jain's equation. So it's a correlation. So correlation will not give you the exact value, it's going to give you a very close value. Okay. So if you use this equation, you're going to get this answer. If you use Moody chart, it will be 0.032 or 0.033. Everything is okay in that, within that specific range. Okay. So this will be F. So now here, if you look here, you have the value of KB, KE, K for entrance, K for exit, K for the bends, you have length, you have diameter, you have friction factor. Okay, velocity is already determined. So you can find out all these as HL, substitute into the main formula, substitute the value of Z2, you can find what is Z1. Okay. So if you substitute all these values, the Z1 will come out to be 136 meters. So that's the solution of this problem. So what we did is that in chapter number 7, we determined, or we were solving the energy equation, but the head loss was given. Now we are actually finding out the head loss based upon our pipe network. How much is the straight pipe length? How many bends? How many entrances? How many exits? How many expansion? How many contraction? So based on these components, now we are actually finding out what are the head losses. In chapter number 7, head loss was given in the problem itself. So now we are moving towards more complicated problems, in the sense that the same problem that we were solving in chapter number 7, now we are solving it here, but with the head losses actually finding out ourselves based upon the pipe network. Okay. So that's the solution of this problem. If this problem is clear, okay, if it's not clear, let me know if there's any point or any step in the problem which is not clear. Then we have another problem here. It's very similar. Combined head loss, referring to the shown figure. Find the flow rate through 25 centimeter diameter pipe. Again, we have to first use the energy equation. Then based on the energy equation for between 0.1 and 0.2, we are going to cancel out some of the terms. Okay. Then after that, we have to look at our piping structure. Okay. So how much major losses do we have? How much minor losses do we have? Okay. So corresponding to the major and the minor losses, we are going to actually find out what is the velocity in the pipe. So this is a problem, you can go through it yourself. it's a similar problem the way we did before. Okay. Then we have a third problem. Again, in this third problem, you see here there is one reservoir A, another reservoir B, but between the two reservoirs, now we have three different pipes. So, but here we have a sudden contraction and a sudden expansion. Previous case, we had two bends. We had one bend, 90-degree, another bend. Here we have the entrance, here we have the exit. The same way as the previous problem which we solved. But instead of having two bends, now we have one contraction, one expansion. That's the only difference. So solve the problem in the same way. Okay. But in this case, there is one more difference. You have to consider the three pipelines. In the previous case, we added the three pipelines together. Here we added the three pipelines, 197. Why? We added 60 plus 7 plus 130 because the diameter was not changing. Now in this case, the diameter is changing. So you cannot directly add the lengths together because this length will have a different velocity, this one will have a different velocity, this one will have a different velocity. So you have to first find out the three velocities using the continuity equation. Then corresponding to those velocities, then you have to sum up all the major losses for the lengths. Okay. So this one will be for the length 1, this one will be for the length 2, this one will be for the length 3. These will be the three major losses. Then you have the minor losses for contraction, minor losses for the entrance, minor losses for one contraction, minor losses for the expansion. This is the minor losses for the exit. Okay. Then add them together, you can find out what is the total losses. Corresponding to those losses, we can also have the effect shown in the hydraulic grade lines and the energy grade lines. This is also mentioned here. There is another problem. Again, I'm not going through this problem because it's a similar format of the problem that we have been solving together. So you can go through it yourself. Okay. Now let's talk about non-round conduits. We have been solving problem for the cases where the pipe is circular. Now, suppose if the pipe is not circular, suppose if it is a duct, rectangular duct. In that case, how we are going to solve the problem? We are going to proceed the same way as we proceeded for the case of the circular pipe, but the only thing is that now we need to find out the hydraulic diameter. Now, this rectangular duct does not have a specific diameter. But if we find out what would be the diameter, if suppose this rectangular pipe was like a circular pipe, then what would be the diameter of that circular pipe? And we call it as hydraulic diameter. The formula for the case of hydraulic diameter is 4 into cross-sectional area divided by wetted parameter. Okay, since we are talking about here conduit, so the entire parameter should be wetted. Okay, so suppose if we have a situation like this, that we have this is our duct, so it has a dimension here L and the width here is W. Okay, so wetted parameter will be 2L plus 2W. Okay, and the area would be L multiplied by W. Okay, so the hydraulic diameter will be 4 into cross-sectional area, 4 into L by W, divided by wetted parameter, which will be 2L plus 2W. So it will be 2L plus L into W divided by L plus W. Okay, so now we have this hydraulic diameter. Once we have the hydraulic diameter, now we will assume that it is not a rectangular pipe, it is a circular pipe with a diameter DH, hydraulic diameter, and we'll solve it the same way as we were solving it for a circular pipe. So in this way, whether you have a rectangular conduit, whether you have a triangular conduit, you have a pipe which is hexagonal in shape, whatever the shape, you can actually find out, you can solve the problems and find out the head losses for it. Okay. Most of the time, the hydraulic diameters are needed for the case of ducts. You see, if we have a central air conditioning, the ducts are normally rectangular. Okay, so the hydraulic diameters are needed there. There are multiple reasons for it. Okay, the most important reason is that the rectangular ducts are easy to be handled. Okay, the circular ducts are comparatively difficult to be handled. Okay, corresponding to the large size of the duct. Okay, because these ducts are not carrying water. Normally, these ducts are carrying air. So we need to have a large size of the ducts. So large size circular ducts will be difficult to be handled compared to the rectangular ones. They fit into the space much compactly. Aesthetic requirement is very important there. Mostly, especially in the construction industry, aesthetic requirement, how it looks like, is very important. Secondly, it saves areas. You can have two rectangular ducts close to each other without wastage of area. You have two circular ducts, there is a lot of wastage in area. So this is now a problem. Sorry. This is now a problem for the case of rectangular duct. Again, a similar problem, but the only difference is that here you have to first find out the hydraulic diameter. Once you determine the hydraulic diameter based upon the length and the width, okay, then you are going to proceed the problem the same way as a circular duct. So you're going to find out the Reynolds number, you're going to find out the velocity first, then you're going to find out the Reynolds number, then you're going to find out the relative roughness, then you're going to go into the Moody chart and find out the friction factor. Then corresponding to the friction factor, you can find out what is the head loss. All the same steps that you did for the case of the circular pipe, you're going to repeat here. The only difference is that in order to do that, because for the case of circular pipe, it was a circular pipe and there was a specific diameter. Now you don't see a diameter. So, but you will find out first the hydraulic diameter. And the hydraulic diameter for this, the formula is this. If you know the length and if you know the width of this rectangular cross-sectional duct, you can find out what is the hydraulic diameter. Okay, so this is again a problem. You can go through it yourself. The last topic is about the pump and the pipe systems. The selection of pump is a comparatively complicated problem. Okay, the thing is that suppose if you have a piping system, okay, so a specific system curve is generated, and that system curve tells that how much is the head needed for a specific discharge. So if you have a specific piping system set up in any building, and you want to find out that what is the pump requirement needed to actually satisfy the pumping needs within this piping system. Okay, so first thing is we generate a system curve, that how much head is needed compared to how much discharge. So the thing is that the more the discharge, the larger the head needed to actually proceed the flow within the piping system. But at the same time, for the case of the pump, a pump curve is provided by the manufacturer. The pump curve says that yes, this is a pump which can generate this much amount of head, but it depends upon how much flow you are making it to pass through. Okay, so if you increase the discharge within the pump, the amount of head that it can rise will become less. Okay, the simple way of thinking is that there is a specific power of everything. Suppose I can take 5 kilograms of weight to the 5th floor. This is my power. Okay, so but if you increase the load, then I won't be able to reach till 5th floor. Maybe I will stop at the earlier floor. Okay, because it's the same power that I have. Okay, so if you increase the discharge, the pump capacity, that how much head it can produce, will decrease. So now what we do is that we have a pump curve provided by the manufacturer, and we have a system curve based on our piping system needs. Okay, we combine the two curves together and find out the point of intersection of them. The point of intersection of these two curves are known as a system operating point. And this is the optimum point at which the performance of the pump would be the most suitable for the piping system that we have, for the fluid pumping system that we have. So we have a system curve and we have a pump curve, system curve based upon the based upon the pumping requirement of the piping system. The pump curve is provided by the manufacturer of the pump. We combine them together. The point of intersection is the system operating point, and this is needed for the selection of the most optimum point for the operation of the piping system. So here, theoretically, this topic is important. Now, what is the thing that you need to know? How do we determine system operating point? How do we determine system operating point? The answer would be we intersect the curves of, so we intersect the system curve with the pump curve. This is the intersection, okay? So we have a system curve and we have a pump curve. Pump curve provided by the manufacturer. That is for the specific pump. System curve based upon whatever the piping that we have where we want to install the pump, okay? So we intercept the system curve with the pump curve, and the point of intersection is actually the system operating point. This is how we determine the system operating point, okay? Both the curves are basically produced on discharge figures, okay? So you have the head versus discharge figure for the case of system curve as well as for the pump curve, and their point of intersection will give you a system operating point. This is a point for you to remember. Example 10.9, you can just skip. We are not covering this, okay? There are two topics here, net positive section head and section limitation of pumps, okay, which is there within your textbook. Yeah, I want you to read it yourself. And with this, our flow in conduits is finished. If you have any question regarding any topic that we have covered today, feel free to ask. Okay, that's it for today.